Thank you, Zoom. So today we're going to be talking about software architecture. Now, how many of y'all have tried to go and look at a tutorial for something like React, and they just show you how to build a simple little counter? Has anyone had that experience? Yeah. Now, how many of y'all have sat down, decided you want to build a real project, and you have no idea where to start? I feel that. Yeah. I appreciate the double hands right there. Makes me feel smarter. Yeah. So what if you decide to just go in anyway and just start coding? You're probably going to get a whole bunch of spaghetti, right? It's like saying, what if you had the tallest building in the world and you tried to go build it without a blueprint? You probably wouldn't have a building. And even if it went up for a little bit, I probably wouldn't want to step in that building anyway. It's just a recipe for disaster because software is extremely complicated. The bigger it gets, the more moving parts you have, which give you more opportunities for something to go wrong. And it just makes it hard to work with if your code is really unorganized. So what are we supposed to do about it? Again, complexity. How do you manage it? Now, if you're a prodigy, and I'm sure some of you guys are here are really good, maybe you can go in and try doing it. I know I'm not that smart. Most of you guys probably aren't either. No offense. It's just a very complicated thing to learn. So for the rest of us, we have software architecture, which is all about how we take large pieces of complex software and break them down into smaller pieces that people can actually work with. It's kind of like building a blueprint for your app. Now, anyone who's been to some of our meetings before might have heard us talk about software design. And that's very similar, where we talked about how it's a blueprint for your app. In case you're wondering what a difference is, software architecture is a bit more high level. So we're talking about how to structure your app at the highest levels, the entire app, while software design is usually about things like how you structure classes, design patterns, stuff like that. I will say that both of them basically achieve the same thing. And one thing that you want to be aware of when learning this type of stuff is that there are a lot of different terms, a lot of different people who call the same thing, call different things the same word, a lot of people who use the same word to mean different things. And it's very easy to get confused if you decide you want to go research some of this stuff on your own after. So do try to focus on the concepts more than what something is named or how to categorize it. It's going to save you a lot of headaches. Now, $1 million question is, how do you do software architecture? Well, you just use other people's architectures. Kind of like you may have heard of design patterns, there are architecture patterns, which are reusable architectures that have been used before for many apps. They've worked for other people, and they'll probably work for you too. And those patterns are built on principles. These are several kind of ideas and guidelines that the patterns are based on. It's good to know these because you want to have an idea of why patterns are structured the way they are, because sometimes a pattern's not going to fit exactly what you need to do, and you might have to go off the script a little bit. Now, what we're going to go over tonight should hopefully be good enough for various types of apps. So if you want to build web front ends, if you want to build back ends, if you want to build mobile apps, or if you're still building desktop apps, then these patterns are going to help you out with some of that tonight. So let's go ahead and start with the principles, the fundamentals. The very first thing, or rule zero, because we're programmers, is to keep maintainability in mind. Now, in general, good architecture needs to be maintainable. Your code needs to be easy to update and fix as time goes on. It needs to be extensible, which means you need to be able to add new features easily. And it needs to be understandable. Can a new person come into your code base and learn how everything works? Now, why do we care about these things? Well, in school, you might turn in your project at 11:59, barely miss the late penalty, and then never look at it again, but that's not how the industry works. You have to maintain what you build in the long term. And eventually, your boss is going to be telling you, when is this feature going to come out? When is this feature going to come out? So on and so forth. And the worse your code is structured, the harder it's going to be to put new features out at a good pace. And that's going to be bad for your performance. It's going to be bad for the whole team. You don't want to be this guy. So the actual rule number one of architecture is you want to limit complexity when possible. Now, I know I said we're showing out how to build complex apps, but you don't want to make things complicated for the sake of being complicated. There's a guy named Brian Kernighan. Some of y'all may have heard before. He wrote the C programming language. He once said, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you're by definition not smart enough to debug it. Now, bit of an ego check there. He's not exactly calling us stupid there, but he's trying to convey something that is also known as the acronym KISS, which stands for Keep It Simple. Stupid. And you really don't want to add unnecessary complexity for small apps. Sometimes you may need to have something whose architecture diagram looks like this. Just make sure that thing is not a calculator or a simple to-do list, right? Don't make things harder than they need to be. And whenever you do need to add complexity, you want to be able to justify why. Say, we're adding this new piece to our code here because X, Y, Z, the code might be too complex to put it all in one place. You might be running into performance bottlenecks. Just make sure you have a reason why other than you read it in someone's blog post. So the next rule is you want to divide your code into independent parts. Now, I'm sure most of us here have bought something on Amazon before. You might be familiar with the search bar on Amazon when you're looking for an item. And you're also probably familiar with the checkout box when you go to give Jeff Bezos your money. Now, these are clearly two separate features here, right? So the code for them should be separate, right? That probably comes off as common sense at first, but different features should be handled by different code. But even in the same feature, right? Let's say you're on iPhone and you're waiting for a message to come in. The code that is drawing the text bubble here should not be the same code that's checking the network, waiting to see if the message has come in yet. Separation of concerns is one of the most important things in building systems that are easy to maintain. And when you can make the different pieces of code independent of each other, you can make internal changes to one part of your code and it won't affect anything else. Just by a show of hands here, who here has been working on a project and it's like you add something new or you make a quick fix and it breaks your code in 3 other places? Oh, I feel your pain. Well, yeah, whenever you can split your code into independent pieces, you have less chances of doing that. And it also makes finding things easier because you can make your changes in one place, right? If I have one part of my app that's responsible for drawing things to the screen, if I want to add something new to the screen, I just go to that part of my app. I don't have to go through 10 different files trying to find what's where. Now, the next rule is that good architecture limits dependencies. Now, this kind of follows from the first, right? If you want to be independent, you don't want to be dependent. But to make sure we're all on the same page, let's talk for a second about what a dependency is. A dependency is when one piece of code needs another piece of code. So for example, let's say we're writing a video game and we have a class called Vector2D, which just stores an X coordinate and a Y coordinate, kind of like from math class. Let's say you've got another class called Player that represents the hero of your game, and they have one of these Vector2 things here to store their position in the world. It tells you where they are. So the Player class is dependent on the Vector2D class, right? If I went and took away the Y variable from the vector class, it would break the Player, right? They'd lose a dimension. I'd flat Stanley them. So whenever you have, the more dependencies you have, the more chances you have to break a class that is dependent on you. Now, the thing about dependencies is that you can try to limit them, but you can't make 2 pieces of code 100% independent of each other because they have to communicate, right? If I build a user interface and have some buttons, but the UI doesn't actually have any data coming into it, then I just have a white square on my screen. It's completely useless. So the question then becomes, how can we allow systems to communicate without sharing too much information and essentially getting them intertangled with each other? You don't want to share too much info. That is a big part of keeping the boundaries between two parts of your system. Now, this is so important that I want to show an example of this gone wrong. So let's say you're building a social media app, right? And for a social media app, you're going to have user profiles. And let's say that you want to add DMs to it. You want people to be able to message each other. So the messaging service is going to be dependent on a user service because you can't send messages without users, right? Now, let's see how this can go wrong with a quick code example. So let's say I have a class that represents the user service, and we're storing our users in an array. In a real app, you'd probably use a database, but we're keeping examples simple. Now, let's say we also had a messaging service. It has a reference to our user service, and we have a function there that will allow us to send a message to a user with a certain username. So you can see we're going to go here, find a user, run through the array into user service, look for a user, and then send a message to them. We don't actually care about the network part of it for this example. Now, this is what we call tightly coupled, as in these two classes are really interdependent. Could anyone here try to tell me what's wrong with this? There's a few things wrong with this, but the worst thing. Yeah. Exactly. Exactly. So for the people on Zoom, he said if you change the data structure in a user service, you also have to change the code in your message service. So right here, we are basically looking inside the user service's internal details. As a messaging service, why do we need to know that information? It doesn't matter to us if they store it in an array or a database or a piece of paper. It's meaningless to us. We just want to be able to find a user. And now, like he said with the data structure, if they switch to maybe a hash map instead of an array, you can't go through a hash map like that. So now our code is going to break. So this is an internal detail, like we said, that the message service doesn't need to know. So how do we fix this? Now, let's go through the user service again. As you can see, we made the user array private this time, right? So now no one else can see it. They don't know how we're storing our users. And we're keeping our internal data hidden. Now we've got another function here called getUserByName. And this allows other classes to get a user, but the user service controls how they can get it, right? No one else knows that it's an array behind there. No other class knows anything. It's just simply, I give you a username and the user service gives you a user. So now when we come back to the message service example, for one, it's a lot less code, right? Imagine if you had to do that array search every place in the app you needed a user. But the real benefit happens when we change the data structure. So let's say we want to switch that array to a hash map. What changes do we need to make to the message service? Yeah, exactly, 0. No changes are required here. And the idea here is that you want to control how different parts of your code communicate very carefully. Now, this function we had here, getUserByName, is something called an interface. Interfaces are basically code that one part of a system exposes to allow other pieces of code to interact with them. Now, don't confuse this with the interface keyword from like Java. It's related and kind of means the same thing, but not exactly. The idea here is that an interface is basically just any functionality you expose that tells other parts of code what you can do and allows them to interact with you, but completely hides the internal detail. It's giving them the what, but not the how. And that's very important. Now, when you have interfaces, You can enforce separation between the different parts of your code. And like we said, keeping that independence is one of the most important things here. You can prevent direct access to any of your code's internal details, and it gives you control over how others access your data. So let's say you want to put some metric that put some kind of count anytime someone accessed a module, right, for logging purposes. See how many people are calling this line of code at a certain time. You can do that because you control how they're getting to that data. So in general, good code minds its own business. And the more a piece of code minds its own business, the less problems there will be when it's time to change something. Now, the fourth and final kind of principle here is don't be a fanatic. Now, with great power comes great responsibility, so they say, and you really don't want to overdo anything with these patterns because over-engineering is very real, and it's one of the easiest ways to get unneeded complexity, which is exactly what we're trying to prevent. You have to remember that what we're going to talk about are patterns. They are not laws, and no one's going to break into your house and arrest you if you don't use a abstract singleton proxy factory bean or whatever that thing is called on the picture there. So just in general, try to remember to do the simple thing first. These are tools, but you don't need a drill to maybe tape something to your wall. All right, so now that we've gotten kind of our ground rules out of the way, let's get into the actual patterns now. So there are, broadly speaking, two types of architectures. You have monoliths and you have distributed systems. Now, a monolith is something that every single one of you has written before, and that just means that everything is running together on one computer. So all of the labs that you've written in programming 1 and 2, they're monoliths. Most of the apps that any desktop apps you might have written, monoliths. And typically this means that they are one code base, so they would be in like one GitHub repo together. And you deploy everything together. So when you want to like download Word on your computer, for example, you just download a single exe, maybe an installer, but it's just a single program that's running on your computer. And it's very widespread, right? Most desktop and mobile apps, at least the clients that run on your personal device, those are monoliths. Front ends on websites, by definition, are monoliths because you have to download everything and run it in your browser. And even most small to medium backends are monoliths. It's good practice to start with a monolith, even if you think you're going to have a big system later. Now, a distributed system, it means that you've taken your app and broken it up so different parts of it are running on different computers. So those different parts of your system are going to communicate over a network. They might be in completely separate code bases altogether. So they might be in separate Git repos. And they can also be deployed separately. So you might release a new version of one part of your system while the other stays the same. Now, the most famous example of this are microservices, which many of y'all have heard before. That is basically whenever you have a backend and split it up into different pieces. There's also peer-to-peer systems which are distributed, such as Bitcoin or any torrenting software that you might have used before. And distributed systems are very complicated. This is apparently a traffic graph of all of the microservices at Netflix. I'm not sure if that's exactly true. I didn't fact check it. But as you can see, it's a mess. And if you work at a big company that has a ton of microservices, it's very complicated. So first thing that we want to establish is don't do this on your personal projects. Distributed systems are hard, and they have a few major cons to them. They're very complex, right? Again, complexity is what we want to avoid here. They're very hard to maintain because you have to coordinate a lot of different systems. They probably have big teams, a different team working on each microservice. And they're really hard to debug too. Did that come in? There we go. My first internship, I had to track a bug from like our front end into like a backend service into like another microservice after that. And I think I fixed it. I don't know, but it sucked. So they're very hard to deal with. Now, of course, there are reasons why companies do that other than to like torture their engineers. So you should know those. Number one is scalability, right? If you take a big app like YouTube that has millions and millions of users at any given time, there's no computer in the world that can handle all of that traffic. So they have to break it up. Eventually, you're forced to use distributed systems if your company is large enough, but that's a very high bar. Fault tolerance is another thing. If you only have one instance of your program running somewhere and it goes down, then your whole business is down. And depending on the kind of company you're running, you can't afford that. And even if it's not like a mission critical system, every second you're down, you're losing money. So don't want that to happen. And also, you can use multiple tools and languages. If you have your app split into different programs, you can have one part of it in Python, another part in Java, whatever your devs want. So there are some benefits to it, but because it's just such a big can of worms, we're only going to be going over monolith patterns today. We may do a distributed systems workshop sometime later this semester, but for now, we're just going to talk about monoliths, which are things that you guys can actually use today. And monoliths are also used in real businesses too, so there is application of this. It's just a matter of having enough time. So for our first actual pattern, let's talk about the layered architecture. How many of y'all have heard of this one before? Okay. I know it was mentioned for like 2 seconds in Intro to Software Engineering, but the idea is that you split your app into layers. And basically, each layer is responsible for doing some kind of technical job. So what we have right here is presentation layer, which is basically UI, service layer, data processing, and persistence layer, loading and saving data. We'll talk more in detail in a second. Now, the user interacts with the top layer. So like we said, the top layer will usually be your UI. And each layer is only allowed to call lower layers. So notice here, even if we're not sure what these do yet, that our dependencies are only going in one way, right? The layer all the way at the bottom knows nothing about the other layers. So that's one way we've kind of contained our dependencies. And our dependencies are only going in one direction. We're trying to avoid two-way communication. So let's look at a real example. Let's say you want to build Notepad. So the top layer might be your UI. So it will be responsible for displaying the text on a screen and showing the buttons that you have at the top. Now, whenever you type, it might handle your input and then call the service layer, which is in the middle. And that's responsible for processing our data, which in this case is updating the text that we have. And then finally, at the bottom, we have the persistence layer, which is responsible for loading and saving data. So if we hit the save button, then this would be the code that saves it to a text file. So is everyone, do we have any questions on this? We're about to talk more about each layer. Cool. So first, the presentation layer, like we said, this is basically your UI. So it presents formatted data to the user, handles user input. And the most common type of thing they have in your presentation layer is a graphic UI with buttons and stuff. But if you're writing a command line program, then the command line would be your presentation layer, right? And let's say you're writing a backend instead. In this case, the code that you have that is processing network requests that are coming in and sending it back to whoever called you, that's your presentation layer because your user is another program, not a person. Do we kind of get that idea? So if you're writing a backend, the net processing network requests, that is your presentation layer. Now, the next layer after that is the service layer. And this is basically responsible for the main logic of your app. Some people call it the business logic layer. And basically, it's responsible for doing whatever your app does. That sounds confusing. Imagine you're writing a calculator app. The presentation layer might draw all the buttons to the screen, but the service layer is what's actually going to calculate 2 + 2. Now, let's say you're doing some kind of image processing, right? And you want to turn a photo from a color to grayscale, then the service layer is going to be the part that's actually making the changes to the pixels of the image. All right. Now, after that, at the bottom, we have the persistence layer. Like we said, this is responsible for loading and saving data to external sources. In some places, it might be called a data access or repository layer. All means the same thing. And most of the time, especially for web apps, this is going to where you interact with a database. So any SQL statements, those would live here. And if you're writing directly to files, this is where you would be handling files. Now, finally, we also have the API layer here, and this is responsible for calling other programs over a network. So let's say you're a front end, the API layer is where you would make calls to your backend and format them in a way that the rest of your program can read. And it's also where you can make calls to any third-party APIs. So let's say I have a project that's getting weather data from OpenWeather API. This could be the part of the code that handles calling it over a network and then formats the data in a way that the rest of my program can read. And I just want to point something out. You might notice that I have the persistence and API on the same level. It's because they're both basically about loading and storing data from external sources. And then finally, this isn't really a layer, but you see it in some places when you look it up. It's called the infrastructure layer. And it basically handles any other miscellaneous things or any kind of external dependencies. So sometimes if you are using an external library and you wanted to write some wrapper functions around that, they might be here. And any general utility functions that are needed throughout your whole code base might be here. Now, one important thing to emphasize is that you might not need all the layers here. For example, if you're writing a front-end web app, you probably won't need a persistence layer because web apps don't store most of their data directly on a user's machine. Instead, they would call the API layer, send that data to the backend, and then it's the backend's problem. So there we go. All right, so as a quick example here, let's say we want to build a backend API with a layered architecture. So at the top, you may have the presentation layer, which in our case, remember, for a backend, your user is another program. So instead of buttons, you're going to have a network interface. That's going to be responsible for receiving requests. And then once everything's done, formatting the data and then sending it back out. Now, after that, you'll have the service layer. This is responsible for processing all of your data. And then finally, the persistence layer at the bottom will load and save everything to the database. And as far as how the actual folders in this project would be arranged, this is how it might look like. So as you can see, we've got the routes folder here. This is the presentation layer. If you look at a backend project and you see routes, that's usually telling you where kind of in your program certain requests can be made. Service layer, again, data processing. Persistence layer, you might be found in a folder called a DAO, which stands for Data Access Objects. I would have just named this folder persistence for the example, but when you guys look in real code bases, there's a good chance you might see the acronym DAO. So just want to make sure y'all know what that means. And then finally, utils handling any other miscellaneous stuff. You can kind of think of that as your infrastructure layer. So now we can kind of do this together because there's only 2 examples here. We're going to look at a couple example apps and see how you might split them into layers. So first, let's say we want to build Microsoft Paint. If I could get a volunteer here, how would you guys split this into layers? Angel. Layers. Mhm. Presentation layer would probably be the window. That is 100% correct. The presentation layer would be your UI, the buttons, and showing everything visually. Would anyone want to maybe try to take a stab at the next layer? Alex. Exactly. So you said keeping track of the pixels and the colors. The service layer is going to be a part that's actually storing and updating the pixel data, right? And then finally, does anyone want to go? Yeah, Brian. Exactly. So last layer would be loading and storing the image to a file. Yeah. Sorry that there's so many big confusing words in this presentation. Just trying to introduce y'all of them here because when you look things up online, it will be even worse and even more confusing. And the way we might structure our project, we might have a folder called views. If you see a folder called views, that usually means you have a UI there, services for a service layer, and then persistence is handling all the loading and storing of data. And for something like Paint, splitting the folders like this might be overkill. This is just for example. Remember, choose simplicity first. Now, the last example for this one, let's say we want to build movie listings for the movie theater. How might we do split this one into layers? Yeah. Exactly. So presentation layer will display everything. So anything that you can see is part of the presentation layer. And then anyone want to take a guess at the last one? So the last one is going to be the API layer. Now, sometimes you could have a service layer in between the API layer and the presentation layer, but all this does really is just loading data from the backend that is really responsible for doing most of the data processing. So for a simple app like this, all we can do is just load and send the data from the backend and then just immediately display it here. So notice how this example only has 2 layers because we don't want to make things more complicated than they need to be. And if you want to break that into folders, it might look like this. So just folder for a UI, folder for network calls. Now, any questions about the layered architecture? All right, cool. So the next pattern is going to be called the modular monolith, which is also called the vertical slice architecture by some people. And with this one, instead of dividing by technical functionality, we're going to split our code up based on features, right? So we're going to divide not by the UI and the data processing and saving. We're going to split things up by each feature. So imagine if you're building a social media app, you might have one module for users, one module for DMs, one module for your feed, and another module for followers. Now, each module is going to be responsible for all of the technical functionality. So we're responsible for the UI, the logic, the data, everything. And the modules function independently of each other. Again, that very important principle here, you want to try to keep things independent. So with the social media example we just saw, this is what the folder structure might look like. As you can see, we have a folder basically for each feature. So followers, messages, posts, users. And one really good thing about this architecture is that you can combine it very well with other architectures. So as you can see here, we've got a persistence layer, a routing layer, and the service layer again. We just went and put the layered architecture inside one of our modules. So this is one, in my opinion, superpower of this architecture because if you need to, you can use different architectures inside each module that you have and almost kind of treat them as different applications. And you can use any architecture inside of a module itself. And that can be helpful if you have a project that is really big. Yeah, so it helps organize large projects. But if you're working on something small, you might not need to have nested folders. You could just split things into features, put your code files there, and that's it. Remember, simplicity first. Let me see. Now, one really big thing about this architecture is that you might be able to convert it to microservices easily if your company needs to do so. And that's because since each module is kind of almost thought of an application in of itself, you should be able to just pull a module out and then move all the code to run on a different computer. And that sounds pretty easy, right? It's not. And if you want to be able to convert a module or monolith to microservices, you have to build them in a certain way. And these things here, you might not need to do if you know your project is going to be very small. But if you are going to go that big, again, this is something I should only worry about in like a company and not like a small company either. One rule is that each module owns its own data. And what that means is that a module cannot directly access data that belongs to another module. So for instance here, let's say that you have the user service trying to get info from the DM service for some reason. It can't just go and get any internal data from the DM service, and it can't even query data from the database directly, right? So this is a bit of a limiting factor because for those of y'all who know SQL, it means doing joins across separate modules is not allowed. And the only way you're able to get data from another module is through a module's public interface. And sorry, I had a brain fart there. What this allows you to do is you could use a separate database for each module if you want, if you're following this, but it also makes things a lot harder. And if you have an app where doing SQL joins are important, then you might not want to follow these rules. And this problem right here brings back a big question, right? If your data is only available from another module, how can we have those modules communicate without tangling everything up and having those dependencies blow up in our face? That was supposed to play an animation. So how do you stay out of dependency hell? Number one, interfaces, what we just talked about. And another way is to use message brokers, which we'll get to in a second. So with interfaces, the only way a module can communicate with another module are true specific functions that are provided for that purpose, right? So let's say we have the user module here. It might have functions like get user, create user, update user, and delete user. And this is the only part of the user module that is available to the outside world, right? Anything that wants to get data from the user module has to go through this interface right here. And other modules know absolutely nothing about how these functions work, right? So we kind of went over this already. And yeah, this is the only way data goes in and out. Total lockdown, no exceptions. If you want to communicate between modules, then you need to do it through an interface. Understood? Now, again, like we said, simplicity first. So how strictly you need to follow this depends on how big your app is going to be. But again, just something to keep in mind. Now, the second method for communicating between modules is called a message broker. And that's actually going to bring us into our third pattern, which is event-driven architecture. Now, notice here how we're going to combine this with architectures. Very important thing to know is that you can combine different architectures together. You don't have to use only one, and we'll see multiple examples of that. So with an event-driven architecture, it is asynchronous, and it uses something called a publisher-subscriber pattern. Some people call it pub-sub, if that's easier for you to remember. And so let's say we have two modules that want to communicate. Instead of directly calling code from each other, you might have one module that publishes a message, and the broker stores it. And another module can be subscribed to messages of that type. And whenever the message is available, module B will get that message and act on it. I think my mouse is freezing. Nope. There we go. So let's say you have an order on Amazon, right? And when you get an order, you usually get some kind of email confirmation, right? So Amazon, they're very big. So maybe if they have a spike in traffic, maybe their email service might get overwhelmed. So what they can do is anytime an order is placed, they can send an order placed event and have that sent to a message broker. And the email module can be subscribed to that. And then whenever that becomes available, that notification, the email module will act on it and send the email out. And the really good thing about this is you see is that these modules don't even know that each other exists, right? The order module doesn't know who its subscribers are, and the email module doesn't know who the publishers are. Now, that being said, one very important thing is that a lot of message brokers are asynchronous, which means that the messages might not be processed immediately. So generally speaking, if you have something that needs to happen as soon as you make the call, interfaces are probably a better choice. So if you need an immediate response, maybe don't go with these. Now, the great thing about message brokers is while you can use them with monoliths, there's something that are mostly seen with distributed systems. So they're often used with microservices a lot. I know we said we wouldn't talk about distributed systems today, but you can use this either way. And something to be mindful of is that there's different types of message brokers. You have message queues, event buses, and they all have their little nuances and differences. So make sure you do your research before you pick one. We're not really going to go any more in depth tonight. And the million-dollar question, again, interfaces or messages? Well, interfaces are probably enough for small apps. Maybe even if you have something that can be done asynchronously with a pub sub pattern. You have to remember our million-dollar rule, keep it simple, stupid. So something else to keep in mind are design patterns. Like we said earlier, good architecture builds upon good software design. And there is something called the observer pattern that allows you to build some simple pub sub behavior without using any external tools. So learn your design patterns, kids. Now, the next architecture is going to be kind of familiar to y'all who have done React before. Oh, sorry, I forgot. We had a quick note. So there's a quick concept here called horizontal versus vertical slicing. What does that mean? Now, horizontal slicing is basically what we saw with the layered architecture, where we're dividing things by technical concern. One part of our code does UI, one part of our code does logic, so on and so forth. And like we just saw with the modular monolith, vertical slicing is when you divide by feature instead. So you might have a module for users, module for messages, so on and so forth. Now, some architectures fit in these categories neatly. So layered, MVC, which we'll see in a second, clean architecture. And some architectures fit into the vertical category. So modular monoliths, component-based architecture, and some don't. But I wanted to point out this difference to you because you can combine patterns and you can also combine the way you slice things horizontally and vertically. For example, like we saw with the modular monolith, right? You can put layers inside of a module. And I think that works great. You can also do something else where maybe you have a presentation layer on top. So all of your UI stuff is one place, but everything outside of the UI might be split into modules. So you can use different patterns for different parts of your app. And I really need to like sell home that a lot of these patterns are kind of made to be used together, and you will be the one to have to make that call. Okay, so now actually the next pattern, component-based architecture. So this is primarily used for UIs. If you've done any React before, the word component probably rang a bell in your head immediately. And let's look at a quick example right here from our own website. This is on the SSD site. We've got some information about each of our officers here. Now, what you might notice is that each of these officer cards are pretty much exactly the same, right? You've got a picture, their name, their position. The way the component actually looks doesn't matter. So a component-based architecture, everything is built from reusable components. And obviously this is good because not repeating yourself is one of the hailing principles of good software design. Now, how do you organize these components? They're organized in a tree, basically. So let's look at an example with YouTube here. So at the top level, you might have a component that represents your entire page, right? And this page might have the sidebar here. It might have the brain rot section, and it may have a section for videos. Now, each of these sections will have components of their own. So in the short section, you might have a component for each individual short, and each short component might have a thumbnail, a clickbait title, and the number of views. So you guys kind of see how that's like in a tree structure? Got it. All right, and this is how you would convert that into a folder structure. So the homepage might have some folders for each section. So something for your short section, a folder for your sidebar, a folder for your videos. And inside the shorts here, we might have one code file for the short section itself and another file for the actual short component. Now, again, how many folders you need to use, that's going to depend on how big your page actually is. Obviously, since the YouTube homepage is huge, it kind of needs to be broken down a bit. But if you're doing something small, you don't need to use a whole bunch of subfolders. So now, folder structure for the entire app. So we just saw what the homepage looks like. And as you can see, we've basically split everything into separate pages, right? Now, and that goes into our views folder, which, like we said, you hear the word view, you should think UI elements. Now, because we've kind of split these among pages, right, we're slicing this vertically because we're basically dividing by feature, right? And like we said, we've got a folder for each page. And we also have a folder here for shared components because you might have things such as the nav bar or the search bar at the top. That's on pretty much every YouTube page. Now, we know that we have these different components, but what work is each component actually responsible for doing? Now, you might have the visual part of it. So it's responsible for determining how your UI is structured, saying, hey, I have a button here. The button is going to be gray and it's going to say free Robux. Now, you might have a part that handles your UI logic. So it basically handles input, stores any state that you might have in a form, and calls the appropriate application logic when a button is clicked. And then finally, you have your application state logic. So this would be, again, the actual data processing for your app. And traditionally, components are responsible for all three of these things. However, sometimes it might be a good idea to pull kind of your data processing out of the component. Now, sometimes it's a good idea to do that. What are those situations? Let's say you're building an app where you have the same data represented in multiple places, and they need to be in sync with each other. So if you have shared state between components that are in two different places, you might want to separate that out and have it somewhere where it's shared. If you're doing a lot of logic and data processing on your front end, then you might want to separate your logic from the UI components. So like we saw with the movie theater example, sometimes your apps, all they do is just call something from the backend. The backend actually does all the work and your job is just to display it. So if that's happening, you might not need to separate the state from your components. But if you're doing something a bit more complicated on your front end, it might be necessary. And if you don't have a backend, so let's say, again, you're doing MS Paint and you have some kind of shared data throughout your application, then you'll probably want to pull out that logic from your UI components. So you can use the components for your UI and then use another architecture for everything else. Because like we said, we can combine architectures together. So you might have a component tree for your UI, but maybe use a module or monolith under it, and that's responsible for doing all the data processing. You could also maybe switch it out with a layered architecture. So you might have your component tree at the top, but when it actually needs some data calculated, it will call the service layer. And then let's say, again, you're doing a web front end specifically, and most of your data processing is on the back end. You could store state directly in components, and it probably won't be too much of a problem. That being said, things like making network calls, I personally think it's a good idea to just have the code for that in its own layer. So that way you don't have to do things like parsing JSON after you got a network request back, and the UI can just call the functions that give you the data. So let's look at the way the folder structure might look when we combine things. So as you can see, for our fake YouTube, we've got a front-end example here. We've got a simple layered architecture. We've got our API layer. We've got some miscellaneous stuff, and we've got our UI folder. But when we open it up, we can actually see that we've got our components inside there. All right, so you see how we've like combined things? Awesome. And then if you want to add a service layer in the middle there because you are doing some more complicated logic on your front end and pull that out of your components, then that's what it would look like. One more thing. I know I said we wouldn't talk about game dev, but this kind of component tree-based architecture is actually very popular for games. So if you've ever looked at the Unity editor, you might notice that you basically have a hierarchy here. There's a more specific version of that called Entity Component Systems that is similar, but not exactly the same as this. So if you're interested, I would learn more. Like I said, it's different, but kind of shares the whole idea of arranging things in a tree. So now for the last major pattern for tonight, model view controller. And this one is almost kind of like a group of architectures because it's got like a whole family. You've got model view controller, model view presenter, model view view model, model view update, model view intent, model view presenter view model, and model view I hate software engineers. Okay, that one might have been a lie, but there are a whole bunch of different ways to do this. And even with just model view controller, which was the original and still most popular version of all of these, people can't agree on how it works. If you ask like 5 different devs what MVC is, you'll get 6 different answers. So we'll show you a couple examples tonight, but just know if you go and research this on your own, you might see things that are a bit different, and that's okay. So long story short, it's another UI architecture for the most part. We'll get to that for the most part later. But let's come back to our component here for a second. So what were the 3 things a component could be responsible for? How your UI looks, UI-related logic, like handling input, and your application's data processing. What model view controller tries to do is separate these. So in short, the model is basically the part that's responsible for your data processing. The view is responsible for how the UI looks. And the controller is kind of a middleman there. It's responsible for handling input and coordinating your UI. Now, to kind of compare this to the layered architecture, you could kind of think of the view and the controller as being part of the presentation layer and the model as being everything below that. Keep in mind, this is not actually how they communicate. This diagram is just for comparison's sake. And the way it communicates might depend because there's actually, broadly speaking, 2 versions of MVC. So MVC was originally intended for desktop UIs and it's still used for mobile development a lot. But it's also being used for web apps, specifically web apps that are rendered on the server. And they work a little bit differently. And it's one of the really confusing things when looking at this architecture. So let's look at them separately. So in the desktop version of MVC, again, you'll have your controller, your view, your model. So the view is the part that the user is going to see, right? Anything that's being displayed, that's the view. Now, let's say they want to click a button, then the controller is what's going to handle that input. Controller will then forward that and call some function in the model, which will update the data, do some kind of processing. When that's done, controller is going to get the updated data from the model, and then it's going to go and update the UI. Any questions? There's a lot of arrows here. Okay, so let's just move that diagram to the left a little bit. One thing about this kind of version of MVC is that the dependencies are arranged pretty good. So as you can see, the model knows nothing about the other parts. The view doesn't know anything about the other parts. Only a section here that has a dependency is the controller, which knows both about the view and the model. Now, one thing to kind of be aware of is there are some different ways to do MVC. So the original version of MVC from like the 70s kind of looks like this. As you can see, whenever a change happens in the model, it updates the view directly, which that might be to your liking, but one thing to remember is that this does have a circular dependency. So things can get a bit more tangled if you do that. For a small app, I don't think it would hurt you, but again, it's up to your decision to make as the developer. And like we said, there are about 100 different variations on how the view might talk to the model or how the controller might work with the view. It's kind of a shit show. So if you see anything else online, it's also valid too. This architecture has existed probably longer than some of our parents. Now, the folder structure is about as predictable as you would think. You've got a folder for your views, models, controllers, but this is only one way you can do it. Like we said, this here is more horizontally sliced because we're dividing everything by technical functionality. Some people don't like this. You can also do it vertically, where basically each component has its own model, has its own view, has its controller. Actually, I should misspeak. Either way, each component should have its own view and its own controller. But the way you arrange them in the folders, you can also divide things up basically like you're using UI components, but then you divide each component into a view and a model. So again, with the example, this is an example using the social media here. You might have a profile page and you might have a view to structure it, a controller for processing UI logic, and a model for any data related stuff. Oh, so that. Okay, I think I duplicated this slide accidentally. Now for the other version of MVC, which is for building web apps. Now, let's look at this one step by step. So we know that whenever you request a web page in your browser and you go to google.com, it's going to call a web server somewhere, right? And that web server is going to send the page back to you. The part of the web server that will get there first is something called the controller, which you can kind of think of this as input handling because your input is a network request, right? So it will maybe process your URL and then go and find some data related to the page you requested. Once that data has been processed and finished, it's going to come back to the controller, and then the controller is going to go to something called a view, which will basically build some kind of HTML page from a template. So whatever data you just got, it's going to put that in a template, build a web page, and then send that completed web page back out to you. So let's look at an example. If, let's say, LinkedIn was built with MVC. So let's say you want to look up SSD's page on LinkedIn. You'll make the request. The controller will extract the input. It'll get the username SSDUF. It'll go to model, which will do some processing, call the database, try to find SSD's profile. It will return our profile data to the controller. Controller will feed that profile data to the view, and the view will generate some HTML code, basically generating our UI, and then send that completed web page back to us. Now, one of the really confusing things about this, especially if you've only done React, is why is our UI structure on the back end, right? I'm just wondering, by show of hands, did anyone else here get confused when they saw that? Okay, y'all are smarter than me. SSD's future is bright. So to understand this, there's basically two ways you can have a web page. There's something called server-side rendering, where you determine your UI structure on the back end like this. And basically, each time your UI changes, it makes a request to the server and returns some new HTML for you. But that HTML is actually generated on the back end. Now, this is contrary to client-side rendering, where your UI structure is determined on the front end, and all of the HTML, CSS, and JavaScript is loaded as soon as you enter a site. And basically, each time you click on a button and get some new data, it's only fetching the data. It's not getting any new HTML. Now, if you've used anything like React, Angular, or any of the kind of modern JavaScript frameworks, they do client-side rendering. So again, that was a part that was really confusing for me because I've done mostly React. So I kind of saw, oh, wait, you can determine your UI on the back end? Mind blown. So yeah, if you ever hear someone talk about MVC, but they're talking about it with some kind of backend framework, just know they are probably talking about server-side rendering. Again, that was something that was really confusing to me. They were like, yeah, use MVC to build your apps. I thought MVC is for UIs. Why are you building it with Node or something like that? Most of the time, it's about server-side rendering. And let me just show you one last thing, and then we'll be done. So as you can see, this might be how you're building a web page with MVC, right? But let's say you wanted to just build a backend, right? Like a REST API that was just sending you straight data. Well, the web server is already using the same technology that a backend uses to send you something. So let's say in our view here, we switch the HTML template with JSON and just send raw data back. Well, congrats, you just built a backend. So some people also use MVC for their backend, even though it was originally a UI framework. So again, one of those things that might confuse the hell out of you if you've never seen it before. Do we have any questions regarding that? Impressive. So that is the last thing that we're going to go over tonight. In case you want to do some more research, there are more monolithic patterns out there, such as CQRS, the microkernel, pipe filter pattern, all of MVCs, everything in the MVC family, and ECS if you're into game development. And that is all for us tonight. Thank you so much for coming out. Turnout was huge. One last thing, if you guys came here and you haven't been in our Discord before, we've got a QR code right there. That's where we announce all of our events every week. We also have an interest survey, so you can let us know what topics you want to see in future workshops this semester. Next week, we're going to be collaborating with DSC to do our deep learning workshop, and we'll be doing an intro to Next.js the week after that. And of course, hackathons are at Marston every Saturday. Thank y'all for coming out. Make sure to finish that pizza. We've got a little bit left. Y'all have a good one.